Hi class, back to talk about the classification of sedimentary rocks. Just like we have varieties of igneous rocks, we're going to have varieties of sedimentary rocks. In this case, detrital, chemical, biochemical, and organic rocks are what we're going to focus on. And then we're going to talk a little bit about their depositional environments and how they're formed in this section. Okay? So if we move right on to sedimentary rocks and the detrital classification, yeah, you guessed it, of course, we have two things we have to focus on. One is grain size and one is composition. And for this class, we mostly focus on grain size. Okay? In this case, grain size refers to the size of the grains, typically in millimeters. Okay? So here we have three sizes: conglomerate, sandstone, and shale. This is very coarse or coarse, this is coarse, and shale would be fine. Okay? So the grain size here, interestingly, is made up of two grain sizes. You can see fine grain material in between, but we're looking at the biggest grain size. That's important, okay, to classifying it, and it's greater than 2 millimeters in diameter. Right? So if it's greater than 2 millimeters in diameter, it's going to be very coarse or coarse. Okay? Sandstone, down here on the right, is going to be less than 2 millimeters to about 1/16 of a millimeter. And then up here for shale, we're having grains that are less than 1/16 of a millimeter, and that goes all the way down to like 256 of a millimeter. So detrital classification, greater than 2 millimeters, we're talking about gravel. Less than 2 millimeters, we're talking about sand. And less than 1/16 of a millimeter, okay, we're talking about clay or silt. Right? So what's interesting here is you have both rock name and then you have sediment size. Gravel is a sediment size. Sand is a sediment size. Silt and clay are sediment sizes. But the rock names here, just like for igneous rocks, we call it a granite or a diorite or something. The rock name, conglomerate, sandstone fits with the grain size, and then shale. Okay, shale is the smallest or finest grain, and you can see here up close. It actually has this one has an impression in it of a fossil, and you can't see up close. You cannot see really any grains here. Right. So you can't see any grains at all. Doesn't look very gritty. It's probably going to be in that shale classification. Where do we expect to find these kinds of rocks, detrital rocks? Okay. Well, they're just made up of broken up sediments, right? And so continental is pretty common. Marine is less common. You find mostly shales there. Okay, but here we have two depositional environments. One is called a braided river, and we'll talk about river systems later in the class. And the other is an alluvial fan. Okay? So you can see all the channels here. This is a continental environment, right? A river system, at least not near the coast, is a continental environment. Down here along the edge we have this interesting shaped structure here. This is called an alluvial fan, and it is also a continental environment. The sand that's coming in here would be coarse grained gravels, okay, and the rocks either would be sandstone on the left. Okay, so remember that's 2 to 1/16 of a millimeter, or in this case sand and gravel, which means it could get big and be over 2 millimeters. The rock names for things that are over 2 millimeters are conglomerate and breccia. Okay? And there they have some additional textural descriptions. Okay? So this is primarily based on grain size. Here's an example of sediments that are detrital. So that's just loose sediments that have to be glued together. They're not made of anything organic. They're just mineral grains that have been rounded and worn down. This one is transitional with fine sand, silt, and clay. This is a delta environment. So this is where we see the river meet a body of water. Okay? You can see the rivers, the distributaries coming in and hitting whatever it might be, a lake or an ocean or a sea. All those are possible for deltas. Okay? All right, so That was detrital. Let's move on to something called bioclastic. Bioclastic rocks are made from fragments that haven't traveled very far in rivers and streams. They have been collected kind of in place because they're made from organisms that were living in the ocean. Those organisms can be microscopic, like this little foraminifera that is in the eye of a needle here. Okay, single cell algae kind of photosynthesizing organism, or animal, so zooplankton also possible. Or we can have big grains or big coral, like that is an example as well. The type of shell you have depends on temperature and water depth, because it depends on where the animal itself or the plant itself is capable of living. But these would be rocks made from the remains of organisms that have died. Okay, where do they get deposited? Well, let's pick a warm, shallow water, clear water environment. So where are we going to find a lot of organisms living and being deposited? Like for a reef, where would we find reefs? In the sort of equatorial regions, right, in the ocean. So we're going to expect them to be marine environments typically. And here's a marine environment. You can see the deep ocean. Well, you can see the reef is here, right? And this is full of organisms that can take the heavy pounding of waves. Behind we have a lagoon, which is where we might find organisms that don't like waves. They like quiet water, okay? And so in the lagoon we get beds or layers, and I'll talk about that later, laminations that form. And then here on the reef itself we might actually find what everyone knows about is coral. Okay? And then you have the deeper ocean sediments out in front of the reef here. Okay? What are the sediments here that make up this reef system? Well, they're all made out of CaCO3. They're calcium carbonate. Okay? There are not many reef-forming organisms that make shells out of SiO2. Okay? But there are rocks that are made out of SiO2 that I'll talk about that are bioclastic or biochemical. Right? Here's a limestone. The most common that we'll talk about here is limestone. It's CaCO3. That's the mineral calcite. Okay? So these are organisms that are taking calcium and carbonate from the ocean. They're making a shell. They're living in the ocean, and they're running through their life cycle, and then their shells and remains are settling out on the ocean floor. As those rocks, like limestone, go through the process of lithification, they will be formed or transformed into this rock, dolomite. So these two rocks are very similar in chemical makeup and origin, dolomite and limestone. One is used, or one ends up not used, but makes the other. So limestone is turned into dolostone, okay, through that process of lithification. It occurs at that time, okay, usually. And the only difference between these two is a simple addition of Mg to the system. So you have Ca, Mg, CO3. Oops, CO3. And we got to balance it, so we have to add a little 2 out here. Okay. The last bioclastic rock, okay, I haven't shown you any pictures of it, is this guy, chert, which you might know as flint. Okay. Notice its chemical formula, SiO2. So of course these would be skeletal remains of organisms that were making skeletons, or their exoskeletons, from silicon and oxygen. Where do they pull that? They pull it from ocean water. They live there through their life cycle, and then they settle out to create sediments on the ocean floor. Okay. If we look at some of the different, grain sizes, I guess you'd say, of bioclastic rocks, all of these are fossil-rich limestones, which you call fossiliferous limestones. Notice you can see the fragments here and here. Notice you can see a fragment there. Those are all shells. And so here's some more fragments. Here's some more shells. You can actually see shells in most of these rocks. So you go from what's called coquina. Coquina is basically all shells, right? It's just fragments of shells. And then as you sort of move to this one, to this one, and to this one, sort of from left to right through this side, you get fewer shells and more fine-grained CaCO3 muds. And so that by the time you get to the last rock here, this one is what we call a micrite. It's mostly made of mud. Not very many shells are present, and you can't really see the shells as well. What's the key to identifying these kinds of rocks that are made from calcite? Calcite reacts with hydrochloric acid. Obviously, I won't ask you to put acid on anything in this particular class since it's not really available to you, but I will ask you, or tell you, hey, this rock reacts with hydrochloric acid, and that would be a useful indicator for you. Okay? Now, third type of sedimentary rock is going to be a chemical rock. So this is again precipitating from water without the help of a biologic organism. So that means basically we're using evaporation in dry climates, arid climates, to concentrate and sort of increase the amount of Ca, SO4, SiO2, Na, and so on. And that will actually lead to precipitation. You can do this on your stovetop. You can pull or put a stove pot with water and salt in it and just let the water boil off, and it will leave the salt behind and it will make crystals. And this is actually what's happening. And where would we expect some of this stuff to be happening? In dry climates where we have salt water available. So where do we have salt water available? Obviously the ocean, but out in the middle of the ocean isn't really a good place to do this. So we need to be in a desert environment, the Middle East. We need to be in maybe the Gulf of Mexico. Right now it's pretty wet down there. Maybe a drier climate than that. Okay. Here's an example of a continental chemical rock deposition. These are the Bonneville salt flats off to the right. They're somewhat famous for being a part of this really hot, dry area of the desert Southwest, and also for racing and setting land speed records. The salt forms through the process of evaporation. Salts are weathered out chemically from the mountains, and then the water creates a shallow lake. Things heat up, and the water evaporates off, so we lose the H2O from the system. Okay? But we're going to keep the calcium, we're going to keep the sulfate, okay? We're going to keep the carbonate, and so you can keep all of those and create salts out here in this hot environment. Famously, if you went to Utah, you could go see the Great Salt Lake, which is a salty lake, just like the Black Sea or the Dead Sea. Actually, not the Black Sea, Dead Sea. Okay, would be an example of that as well. There are other ones here as well. There's one in sort of down here somewhere called Mono Lake is a pretty famous one. Okay. Types of rocks we get from this, well, they're called evaporites in general, but halite would be one of them. Gypsum would be another. Those are two minerals that would produce rocks. What's the difference between these rocks and, let's say, what's another difference texturally between these rocks, biochemical rocks, and detrital rocks? Detrital rocks, we focus a lot on grain size. For biochemical rocks, we're interested in their composition, and whether we see shells and they react with hydrochloric acid. And then for chemical rocks, we're mostly interested in their composition. Grain size is less important. These will be made of grains that grew together, crystals that grew together. So they'll look less like fragments of individual grains that were glued together. You'll see fewer grains and more crystals in these types of rocks. Okay. The last type of rock strictly speaking, doesn't fit the definition of a rock. It is made of organic material. It is part of a transitional or continental depositional environment, and it's organic. Okay? We are talking about coal. If we take woody plant material and we bury it, it's here, sorry. So we take this stuff that's fibrous and tough. This is different than oil. Okay, it's different than gas, but the fibrous, tough, woody material, we put it into water, it's going to consume oxygen through the process of decomposition. But in a swamp, the water is stagnant, so there's no flushing of oxygen into the system. So what will happen is that the decomposition process will only make it a limited to a limited degree, and there will be a lot of material left over with very little oxygen. As more sediments are buried on top of that, this stuff actually gets preserved. Okay, and as it gets preserved, it gets buried through the process of lithification. You start out with something called peat, where you actually have like leaves and twigs and stuff that are really clearly present, and you can find examples of peat in Ireland and in England, and it's a fuel, an inefficient fuel that you can burn or use to heat your home. Okay? If we bury it and compact it a little bit more, it turns into lignite, which is sometimes called brown coal. Pretty dirty, pretty bad for the environment to burn brown coal. A lot of sulfates, and that creates a lot of contamination. Compact it and bury it a little bit further, and we end up with bituminous coal. This is pretty efficient in terms of having a lot of energy per pound. That's what I'm talking about when I talk about efficiency, right? It's rich in carbon, and so if you want to think of this as low carbon, because it's got a lot of other junk, if we cook it even further, it's going to end up being almost all carbon, and this will be high carbon here when we get to anthracite, and it's going to have the most energy per pound. Most of the coal we burn in the U.S. Is going to be here bituminous, and there are some restrictions primarily because of sulfate restrictions placed on coal-burning coal-fired power plants. That they don't want to burn lignite because it's too inefficient and too dirty. It's too hard to clean it up. So bituminous coal is preferred, and anthracite, which is probably the least common of all of these, would be the most efficient and least damaging to the environment. All of them put out CO2, and that's not something a coal-fired plant can stop. They can stop nitrogen oxides and sulfur oxides from leaving the system. Okay, so coal, unlike oil and gas, is made from woody plant material, typically in that depositional environment that's transitional, okay, where we have both water, abundant water, and plant material. The process of making it is not unlike making oil and gas, with just different starting materials, and of course we have to heat it up to get this process going, so we got to bury it, and that means putting it down into temperatures or pressures that are around 100 degrees Celsius. The average geothermal gradient, we'll talk about this a little bit more from igneous rocks, and when we talk about metamorphic rocks, is a temperature increase as you go down about 25 degrees Celsius. So that means you're going to need about 100 degrees, you're going to need about 4 kilometers. You have to bury this material about 4 kilometers to get it up to the temperatures we need to see coal forming. Now, coal is going to form throughout the process, but sort of to make sure it's sort of fully cooked. Okay, so all the rocks we've talked about fall into different kinds of depositional environments. And you'll remember I talked about the 3 basic kinds: continental, transitional, and marine. Okay, so where do we find coal forming? Find it here in a swamp, okay, which is sort of in that transitional, possibly marine environment. Where do we find, let's say, evaporites? Okay, arid, restricted circulation. Okay, so we have water come in, but we don't have a lot of water moving in and out, so we end up with high evaporation because it's a dry climate, and we're going to get evaporites here, okay, potentially in this transitional environment. But I showed you how they could also form in a continental environment. Okay. Types of continental environments: streams would have sands and gravels in them. Lake environments typically are continental, and they are continental, but they tend to have very fine-grained sediments in them. And we didn't really talk too much about ice, but ice has its own set of rocks as well. Reef would be clearly marine. Those rocks would not be detrital rocks; they would be biochemical or bioclastic rocks. Okay, so we have organic, biochemical, we have clastic, and then we would have chemical rocks, right? All 4 of those different rocks have different kinds of depositional environments. They're not necessarily unique to one, but and I'll talk about how we can identify that a little bit later. Okay, so that wraps up our summary on the 4 basic kinds of sedimentary rocks, how they form, and roughly kind of how they're linked to depositional environments or where we'd find them. Detrital, biochemical, inorganic chemical, and organic.